Hi everyone! In this last video for this chapter, we're going to talk about nitriles, which is our last set of carboxylic acid derivatives. So let's talk about how to prepare nitriles. So again, there are a couple different ways to do this. You could start with an alkyl group that has a leaving group attached. So this could be an alkyl halide, so maybe that leaving group is a chlorine or a bromine. Or it could be a tosyl group, so you could have the tosylate group there. And then you can react that with sodium cyanide, and the cyanide group will be negatively charged, so that will act as a nucleophile, and that will come in and attack the partially positive carbon next to our leaving group, and then the leaving group will leave. So this would be an SN2 reaction. And what you get at the end is our nitrile. Now, of course, this reaction involves cyanide, which is a poison, so it might not be the best option available. Let's just make a note. Cyanide is a poison. So another way that we could prepare a nitrile is by using our amide that we just talked about in the last video. And we're going to use thionyl chloride, SOCl2, to then make our nitrile. Now we also do end up with sulfur dioxide gas as a product. And we also form hydrochloric acid. So there are some byproducts for this reaction. So let's look at the mechanism for the second reaction. So again, we're going to start with our amide. And this amide does have a resonance structure. So we could move the lone pair on nitrogen over to create a double bond, and that will move electrons up to oxygen. So then oxygen will be negatively charged in that resonance structure, but in the hybrid structure, it has a partial negative charge. So because that oxygen has a partial negative charge, it can then attack the sulfur atom in our thionyl chloride molecule, which will be partially positively charged. And then that's going to move electrons up to oxygen on thionyl chloride. And we end up forming kind of an interesting intermediate here. So let's see, we've got our oxygen atom that's now bonded to sulfur. Sulfur now has a negatively charged oxygen and two chlorines attached. And then we still have our double bond to nitrogen. Okay, so notice that those chlorine atoms on sulfur could act as leaving groups. So the oxygen atom is going to reform its double bond to sulfur, and that's going to kick out one of the chlorine atoms. So then we end up forming let's see, this intermediate here. Now, in the next step, we're going to lose one of the protons on nitrogen. So most likely we have some sort of base coming in, like chlorine, and it's going to come in and take one of those hydrogens from nitrogen. So we can just write minus H plus here. And I'll just highlight the hydrogen that we're losing. Okay, so now nitrogen is neutral again, and the next step involves nitrogen forming a triple bond. But first we need something to take the hydrogen from nitrogen, that last hydrogen. So again, we're going to lose a hydrogen atom, or a proton. And again, there's, a base that's going to take it, so maybe chlorine. Let's see. So then we're going to form the following. Okay, so now at this point, nitrogen can make its triple bond. That is going to then actually kick out oxygen, and it's going to create a double bond with sulfur. And chlorine is going to also get kicked out there. So there's a lot happening in this one step. So what we end up with is that alkyl group bonded to carbon, which now has a triple bond to nitrogen. We've also formed SO2, so sulfur dioxide gas, and we formed hydrochloric acid. Okay. Now let's look at some reactions that nitriles can perform. So as we've often talked about, we can perform hydrolysis, so that will take us kind of back to our original starting materials. So if we have our nitrile group, we can go back to the amide by using acid and heat. But we could also go all the way back to a carboxylic acid if we further perform hydrolysis on the amide. Now, the other way that we could get back to that carboxylic acid is by using base hydrolysis. So we could also use sodium hydroxide and heat, as well as acid at the end to protonate the oxygen on the carboxylic acid. Okay, so another reaction that we could perform with nitriles is one involving Grignard reagents. All right, so let's say we have our nitrile group or molecule, and we're going to react this with a Grignard reagent. So remember that alkyl group on the Grignard reagent is negatively charged, so it can act as a nucleophile. And it's going to attack the carbon atom in the nitrile molecule. That's going to move one of our pi electrons, or one set of pi electrons, back over to nitrogen. So now carbon has a double bond to nitrogen, which is now negatively charged because it has two lone pairs of electrons. Typically, nitrogen likes to just have one lone pair to be neutral. And we've also added in our other alkyl group. And I put a little prime symbol next to that alkyl group so we can keep track of the differences. So now in the next step, we're going to add some acid here, and the negatively charged nitrogen will protonate itself using that acid. So now nitrogen is neutral. And we're going to again add another round of acid. But first, what is this intermediate called? Do you remember? This is from our aldehydes and ketones chapter. This is called an imine. All right, so let's add that second round of acid here. So again, nitrogen can grab onto a hydrogen from that acid, and that will give us a positively charged nitrogen. Okay, so now that we have used these acid molecules, we do have water hanging around as well. And that is going to act as a nucleophile and attack the central carbon there, which is going to move pi electrons up to nitrogen. And now we have a tetrahedral intermediate like we've seen before. So on one side we have an amino group, and on the other side we have our water group. Now we're going to do a proton transfer, so we're going to move one of the hydrogens on our water group there over to nitrogen. So we can just say plus minus H plus. So now we have an alcohol on one side and ammonia on the other side, which is a good leaving group. So the oxygen atom on our alcohol can form a double bond, which will kick out that ammonia group. So now notice we have a carbonyl group again, but here we have a hydrogen attached, so that ammonia molecule that just got kicked out can grab that proton from oxygen. And we form a ketone and the ammonium ion. Okay, so if you need a ketone and you have a nitrile handy, you can perform this reaction with a Grignard reagent. Now let's look at a reduction reaction with nitriles, and this will be pretty similar to amides. So if we have a nitrile molecule and we react it with our handy lithium aluminum hydride in excess, followed by water, we're going to form a primary amine. So pretty similar to what we've seen before. And in fact, let's look at the reaction map for nitriles. So we just said that we could form nitriles using either an alkyl halide or a tosyl group in place of the halogen. We also said that we could form nitriles from amides. So we saw that in the last video as well. Let's see, we can also form a carboxylic acid in two different ways. Starting with a nitrile. We also saw that we can form a ketone and a primary amine. So pause the video and see if you can fill in all of the missing components here, so the blank arrows. And when you're done, you can unpause the video and we'll go over it together. Okay, so let's fill in those missing pieces. So earlier we said that if we start with an alkyl halide, we can use sodium cyanide to create our nitrile molecule. But remember, cyanide is a poison, so it's probably better to avoid that reaction. We can also use an amide and thionyl chloride. So we went over that mechanism. What are the two different ways that we can form a carboxylic acid from a nitrile? So they're both hydrolysis reactions, but one is acid hydrolysis and one is base hydrolysis. So in acid hydrolysis, we just have acid and heat. In base hydrolysis, we have sodium hydroxide followed by acid to protonate the oxygen at the end. And then how do we form a ketone from a nitrile? So we said we would use a Grignard reagent followed by water. And remember, water acts as the nucleophile. And, or it acts as the nucleophile in the second part of the reaction. And then finally, how do we make our primary amine from a nitrile? We use, oops, I went back a slide and showed you the answer. So we use lithium aluminum hydride in excess, followed by acid. Or water. Water or acid, either one really works. All right, so again, some of these reactions are pretty similar to reactions we've seen before with carboxylic acid derivatives. My recommendation is to really just go over the acid halide reactions because those will be really similar to reactions that we perform with our other derivatives. But there are a couple of exceptions, so remember if you want to stop at an aldehyde, you need a special reducing agent, and esters need a different reducing agent compared to acid halides, for instance. So there are a couple of exceptions and reactions that are slightly different, but for the most part, a lot of these are the same. Again, at the end of your chapter in your textbook, there should be reaction maps for each of the different derivatives. Those are really useful to go over. You can kind of recreate them on a piece of paper, but leave the reagents out or leave the products out, and then see if you can fill in the blanks. That's always a good exercise to do. I also posted flashcards for all of these reactions we've gone over with the derivatives. So if you do learn well with flashcards, definitely download those and work through those. See if you can figure out what the reagents above and below the arrow are, or what the product is. Okay, now if you have any questions, always feel free to message me or set up an office hour using the Calendly link on the main page of Canvas.